Check this out though. So we're in this room all the time. So today, it would not stay down. It's like, really? So I don't know. I'm like, this is just crazy. So we've been talking about chemical equilibrium, and now we're going to talk about something called LeChat's principle. And LeChat's principle is something you can eyeball, and we'll see you can kind of quantitatively approach it too, but you can just qualitatively approach it, just kind of eyeball it. I thought I had this. Oh, it doesn't want to go. All right. Well. Whoa. Doesn't want to do anything. So you're going to see this whole A plus B goes to form C and D. And we know that we can write an equilibrium constant expression, okay, for it. So LeChat's principle applies to systems in equilibrium. Reactants on the left, products on the right. Cool thing about chemical equilibria is you can go ahead and switch them anytime you want to, because they're going left and right to left. And what this says, it's almost a human thing. It says if you take something that's minding its own business, the amount of reactants and products you have it's at equilibrium, they're constant, you multiply them through, you get your Kc. If you stress that system, okay, then something's going to give. Your equilibrium's out of whack. Oh, it's started working. So what do we mean by a stress in a chemical equilibrium? Well, here's a list of them in italics. First off, we can sprinkle it with some more reactant or sprinkle it with some of the product, and that would stress it. It's going to have to adjust. Another way to stress a system that's in equilibrium, minding its own business, is to change its temperature, and we'll kind of talk about that effect. If the species are all in their gaseous state, which we talked about, we did an example where NH3 was formed from H2 and N2. Hey, it happens. There are chemical equilibria out there where everything's in their gaseous state. If we monkey with the pressure, it has consequences. That's stressing the system. Similarly, changing the volume when everything's in its gaseous state. Okay, so I'm going to kind of talk through what that looks like. So these are stressors. Let's start with the first one. Let's change the concentration of a reactant or a product. So this is our generic, two reactants, A and B, going to form two products, C and D. The lowercase letters are their stoichiometric coefficients. We could come up with, remember we talked about, so long ago, what's today? We talked about it Monday. We said you can have your equilibrium constant expression, Kc, but that's specific for equilibrium concentrations. I call this the snapshot, your reaction quotient. You can do that for any concentrations. And at equilibrium, you have your Kc expression. Your Qc and your Kc expression look identical. But again, this is at equilibrium, and I kind of made a deal out of it. Sometimes I would put little subscripts E's here. These are the molar concentrations at equilibrium. This is a snapshot. So what if your snapshot, your reaction quotient, is equal to Kc? What then? It's at equilibrium. Exactly. Okay. So let's just say it's at equilibrium. We're going to stress it. The way we're going to do that is we're going to increase the concentration of A. So it's at equilibrium. We're going to increase A. Now, the other day we talked about this. Let's see if I don't have my little marker. Maybe my finger will work. Here's my A. Oops. I don't think it's going to work. If we increase the thing that's on the bottom, what will happen if we increase this value? What will happen to Kc?
Smaller.
It gets smaller, exactly. Actually, I was pointing at the wrong one. Kc, as long as we keep the temperature constant, will stay the same. But over here, let's go over here. They were equal. Now I'm going to take this, increase this. Jacob says if I increase A, Qc is going to get smaller. That's right. And we said last time, if Qc is too small, then we need more of what's in the numerator, and what's in the numerator are the products. I kind of think through it that way. That's exactly what we're going to see. According to LeChat's principle, when you increase A, then everything's going to have to change. A, B, C, and D are going to have to change. It will temporarily be out of equilibrium. And in this case, we need more products. So the reaction will actually go what we say from left to right. It will produce more products. The more detailed way of looking at it is when we substituted in, when we jacked up that A, what that made, that Q was small. And so Q or QC was less than K or KC. And then just like we talked about the other day, if it's too big, if it's too small, we need to pour more products. So then again, I haven't used any numbers here. It's just eyeballing it. It's just kind of thinking through what will happen to the quantity, okay? So in the big picture, in this particular scenario, if you have this on a test or whatever, if I increase A, okay, notice I'm going to have to push it to the right. That's going to increase the molar concentration of C and the molar concentration of D. It just will. A will be greater at your new equilibrium. What do you think about, well, it's actually already in your notes. Can you see where the other reactant, B, is going to have to be smaller? It will be smaller because it made more products and it had to use that B up. So the only one that got the short end of the stick in this case was the other reactant. Okay, but when the dust finally settles, again, your KC is not changing. Your QC, your snapshot, temporarily changed and rearranged, and then eventually, given enough time, your QC again will equal your KC. That's the way I think of it. Very good. So what if we, and that's Le Chatelier's principle, that's totally Le Chatelier's principle. One of the things about Le Chatelier's principle is I think of kind of a pushing and pulling sort of thing. So I'm not gonna write that, well I could, but here's my chemical equilibrium from left to right and from right back to left again. We'll go ahead and do, I have AA, BB, CC plus DD. Okay, so a minute ago, and I'm changing my scenario, but a minute ago, do you see where it's a push? If I add more A, and we can think through it quantitatively, we said that QC was too small, we need to increase it by forming more products. We could also think of it as a push. I increase A and I push it that way. It'll also work for you too. Now, I'm changing my scenario. Instead of adding A, I'm going to remove A. So now it's going to be a pull. So I'm going to take A away and I'm going to pull. And actually, when we think through it, you're going to see that the numbers work out that way too. Okay? So if I take A away, okay, then, where's my pen? I'll just write one of them if that's okay. I'll write my snapshot. Okay, so if I take A away, what is going to happen to the value of QC? If I'm making the denominator smaller, it will go up. Yep, your QC will be artificially too high. And what we said, if your QC is too high from your KC, then you got to get rid of what's in the numerator, and what's in the numerator are the products, and that's the pull. You know, that's Le Chatelier's principles. The way of stressing it by adding or removing reactants or products can be thought of as a push or pull. Oh, see, I guess I did have that. So in this case, we're taking A away. Okay, QC will temporarily be too large, and to make it smaller, we have to have our products go back to form reactants. Okay, so that's kind of either push or pull, or kind of think of it, or a hybrid of these two things. But your system will be out of whack. It'll be out of equilibrium, which is fine. I just don't memorize these things, though. I think through them. So in this case, does this make sense? Now, this is the second scenario where we're taking some A away. Sometimes what I do is If the arrows are the same length, that means that the rate in the forward direction is equal to the rate in the reverse direction. This case just a minute ago, we said that it's going to have to proceed from products back to reactants. We could kind of show the temporary sort of out of whackness that way, where I'm just showing the arrow longer, going from the products back to the reactants. So bottom line, when the dust finally settles, the new equilibrium is established, we're going to have what? Less C and D, okay, and less A. Yeah, because we took some A away. But can you see where we're going to have more B? If there's a happy side to this. Okay? So that's kind of stressing the system. And in today's lab, you're actually going to be seeing that with colors. So I'll just go ahead and give you a heads up. That's the beauty of doing this lecture in the NAT lab, is that pre-lab will be significantly shorter than if we hadn't done this. So the way today's lab is going to work is this is going to be one color, and this is going to be another color. It's kind of fun, short but fun. Okay, so again, when the dust finally settles, your QC has to go back to equaling your KC. In this universe anyway. Okay. Can you qualify? Okay. So again, I mentioned on a test to be able to do this. However you're, again, I probably wouldn't memorize it. I'm just trying to understand what LeChat's principle does based upon what you know about chemical equilibria. So if we increase the concentration of a product, oh, you guys don't have the answers to this. So what happens if we increase C? When the dust finally settles, which direction is it going to go if we increase C? It's going to go to the reactants, yep. So when the dust finally settles, what's the molar concentration of A and B going to be? Increase or decrease or the same? Increase, perfect. What about the molar concentration of D? Decrease, it will decrease. We're increasing this, pushing it that way, D is going to decrease. Yep. Perfect. Well, what if we took some of C away? I like the whole pushing pulling thing. It just really works. What if we take some C away? What direction is going to have to favor?
Products.
Yep, favor the products. And you could think it through by how that affects the QC and all that, but it's going to pull this way. Yep. So when the new equilibrium is established, what will happen to the concentration of D? Will it increase, decrease, or be the same? Will increase, perfectly. How about A and B?
Decrease.
They will decrease. Yep. Because they don't know it. Yep. It's that pull thing. You know? So taking something away is pull, adding something is a push. These make more sense on the next few slides, and actually I added a little bit. And I'm thinking some of the chemistry that's going on with this color, remember a minute ago, I told you in today's lab, basically you'll have two different colors. That's what's being shown here. So for instance, and I'm pretty sure, yeah, this is one of the things that you guys are going to be doing. If I had my little stylus, I would write tan over here, or brown, and I would write red here. Sometimes they call it blood red. So this is red. Okay, this species is tan. Okay, all they're saying is that you can take iron 3, minding its own business, and if you add cyanide, thiocyanate, okay, because that polyatomic anion, it makes this is called a complex. I don't think we've talked about that much. This thing right here, it's not an ionic compound, it's a complex. Where you have one Fe3 plus and one SCN minus 1. So it has a net charge of +1. Anyway, this is the blood red complex. So it turns red. Equilibrium, right? So I guess the only stressor comes in this middle one, where what we've done to get this color, oops, my builds aren't working. Maybe I didn't save it. Well, I think that's what happened. So from left to right, what we're doing here is adding, we're adding, what does AG stand for?
Silver.
We're adding silver, and the silver is removing some of the thiocyanate. And as it does that, and I wish I had my other equilibrium, look at your equilibrium on the previous slide, as it does that, it pulls this way. And what color is the Fe3 plus by itself? It's the tan. So it's kind of a fighting the chemical equilibria by adding a new equilibria, which I'm not a fan of, to tie up one of the reactants. And it's Le Chatelet's principle. Removing SCN minus, it goes this way. So anyway, I think today's lab will be even better than that little thing. Okay, so to stress a system that's in equilibrium, you can change the concentration, you can kind of sprinkle a little bit of reactant product, you can remove a reactant product various ways. Now, what about the effective temperature? Because you're actually going to see that in today's lab too. The effective temperature is a little different in that not only do you stress the system that's out of equilibrium, by golly, like the slide says, you get a different K. You get a different KC. KC is temperature dependent. Okay. We've talked in here a fair bit throughout general chemistry about endothermic, exothermic reactions. If something is endothermic, you put heat in. So we can consider heat a reactant, endothermic heat in. Now, I like the effective temperature on chemical equilibria. I think the push-pull thing really works here. See what you guys think. So this is our snapshot, our reaction quotient. This is our at equilibrium. Okay. So, if it's endothermic, I think we're all okay with this. We think of heat as a reactant. In this case, if we add heat, it's like adding a reactant. So I'm going to ask you this way. Are we pushing or pulling? Pushing, exactly. So if we're pushing, we're actually going to establish a new equilibrium. And if we're pushing, your C and D is going to be higher. So what's that going to, consequence is that going to have for your KC? It's going to be a new one. It's going to be higher or lower? Higher. That's the rule of thumb, and however you get there, that's how it works. Again, I don't memorize things very well. Endothermic equilibria, you increase the heat content, increase the temperature, heat it up. Okay, you're going to form more products, and you're going to have a new KC, a higher KC.
Does it change the A and B at all?
Yeah, what do you think it would do to the A and B?
Decrease it?
Yep, it would decrease it. Your new KC would have a higher equilibrium concentration C and D, less of A and B. Yep. So endothermic reactions. So down here I kind of have what you just told me. Your new KC will be greater at a higher temperature, but that only works for endothermic equilibria. Your old KC at the lower temperature will be less. All right. Well, if we did endothermic, we've got to do exothermic. Exothermic, your solutions get hot, so we're going to put heat over here on the product side. Okay, there's our snapshot reaction quotient. There's our equilibrium constant, Kc. Let's go ahead and heat it up again. So if I'm heating it up, what am I doing? Would we push or pull? What'd you say? Pull? Why'd you say pull? I agree. Well, we pull from this side? Yep, I agree. Sierra's thinking that I would actually go over here and push, which is the same thing as Sierra is going over here and pulling. Okay? That makes sense? We have the same thing. Any questions about that? Adding heat, exothermic. So which direction is it going to go? Yep. Back to the reactants, exactly. So if we increase this number, or these things in the denominator, what's going to happen to your KC? It's going to get larger or smaller? It's smaller. It will be a new KC at the higher temperature. But this is just the opposite of what we saw for endothermic equilibrium. For exothermic equilibria, and that's kind of why the Chatelet's principle is happening behind the scenes. For exothermic, as you increase the temperature, okay, it's going to lie further to the reactant side, which they're in the denominator of our KC expression, so it's a smaller one. So at your higher temperature, your KC is going to be smaller, lower temperature. Push. All right then. So that's two ways. We said you can add, subtract reactant products, you can change the temperature. Now here's another one for you. What if we change the volume? Actually, the last two, I don't think I necessarily need to talk about pressure. This one has to do with things that are only in their gas. The equilibria, the reactants and products all need to be in their gas phase. And there's a lot of those out there. The NH3, the formation of from N2 and H2, that was an example. Well, I think we're going to look at that here in a minute. So you'd be like, all right, oh, okay. And actually, I think, like I said, this is the one we're going to look at as an example. Here's my confined box. We've been talking about this. I think they call this the Haber process. In equilibrium with ammonia, NH3, well, everything in their gas states. I won't put G's there. You'll have to just take my word for it. And we'll go ahead and balance this by doing that. That looks good. So we have all these particles. And if I had 3 different colored markers, I would put 3 different dots in there because I have H2, N2, and NH3. And all I'm going to do, if it's at equilibrium, is I'm just going to change the size, change the volume of the box. That's it. You'd be like, well, what does that do? Well, it changes the moles per liter of the reactants and products that are there. So, in PV equals nRT, we did this the other day as a proof. We can get to molarity, which is what those brackets mean, by taking moles per volume. And we rearranged that the other day and came up with something with regard to, we came up, remember Kp, how it relates to Kc. This is going to kind of be reminiscent of that. So we can go ahead, if the molarity is moles per volume, we can go ahead and take our molarities and substitute moles of C per volume, raised to the C, moles of D per volume, raised to the D, etc. Moles of A per volume, raised to A, moles of B per volume. Now, one of the things about here is those V's look great. They look enticing. You're like, dude, all my V's cancel. But remember, they do not. Because actually, these are raised to a power. Now, if your A, B, C, and D were all 1s, they would cancel. Okay? So you can't count on that. So if we pull out our 1 over V term, it looks like this. So now we have the relative number of moles raised to stoichiometric coefficient times the inverse of volume raised to this mess up here. And all where these stoichiometric coefficients, well, they are. But the exponent of the inverse of V, all they came from was C plus D minus A plus B. That's it. And this is actually, I don't know if you remember clear back when we talked about getting to Kp, how it relates to Kc. I was like, well, let's clean this up. I don't like that inverse of V, and actually we're going to do that here in a minute. So we can clean up the inverse of V by taking its power through by -1. So now it looks like this. Where here we have the moles of those things raised to stoichiometric coefficients. Now simply times the volume, but notice it's raised to a power, and the difference between its power is I multiply through by a -1. That's it. This quantity versus this quantity. Again, little a, the little b, the little c, the little d are stoichiometric coefficients from the balanced equilibrium. And I don't know if you remember, but clear back seems like forever ago when we talked about Kp, we called this guy up here, we call this delta n. Remember that? Delta n. Change in moles. Okay, well, if that's okay for you then, now let's go ahead and start monkeying with our volume. So let's just say, let's go ahead and increase volume. Well, if we increase volume and we're looking to see what effect it will have, and one of the things I don't like about this slide is I wish, and I did on my thing, so I must not have saved it because I restarted my Surface Pro because it stopped working because I wanted to take a picture because I needed to erase the chalkboard. So anyway, so what I would have put, and you can if you want to, put QC right here, QC, because that's a snapshot. QC is equal to, and then how do we know what QC is equal to? It takes the same form. So QC is equal to this mess right here. QC is equal to n sub c raised to c power, n sub d raised to d power, divided by n sub a raised to a power times n sub b raised to b power, times b raised to the quantity a plus b minus c plus d. That's our snapshot. I thought that was important enough to copy that over. Because when we stress the system and we increase v, what this is saying is that assuming that we have a positive power it's being increased to, or a positive power, how do we get a positive power? Well, your a plus b, the stoichiometric coefficients of the sum on the reactant side need to be greater than c plus d. If that's the case, your Kc is going to increase, or your Qc, excuse me, is going to be too big. And one of the things we learned last week, that if you have a QC snapshot that's too big, you have too much products. So if you have too much products, then it needs to go from products back to reactants again. That's it. Now, I did all this proof and I feel a little bad because I'm going to show you a shortcut that is, but I'm just kind of showing you behind the scenes. So now, if you have a negative power volume, how would you get a negative power volume? Well, you would if your coefficients, a plus b, is smaller than d plus c plus d. It'll be negative. And so if you increase, which we're increasing volume, something raised to a negative power, then it will make it smaller, right? Your QC will be smaller. If your QC is too small, that means if your QC is too small, then it means you don't have enough products, so it will go over that way. So your reactants must be converted to products in order to reach your new equilibrium. Now, I didn't say it explicitly, but if I were just to generally ask you, does your Kc change? Curious. No, you're right. Kc does not change. The only time we said Kc changed with the temperature. Same Kc value. Perfect. So anyway, I told you I feel a little bad because here it is in red. The whole thing I talked about, basically. If we are increasing the volume, which is what I just talked about, it kind of makes, I don't know, not that it makes sense, but it's like, I'll buy that. If you increase the volume, you look on your reactant side, you look at the moles, like added stoichiometric coefficients. The moles on your product side, the stoichiometric coefficients, whichever side you have more of, that's the side it's going to go to by increasing the volume. That's it. Increasing the volume favors the formation of the substances that occupy more volume. That means that you have the stoichiometric coefficients add up to a higher number. So what do you think? If we increase the volume here, which side would it favor? How do people think that it would favor the reactant side? How do people think it's the product side? You guys didn't vote. It is the reactant side because if you increase the volume, we have 3 over here, we have 2 over here. Increase the volume will favor the reactant side.
Like
that's
pull,
it.
then?
What's that?
Is it like a pull then?
It is a pull. It is a pull. Yep. You got it. We have 3 moles over here, So, yep, it's gonna go over to the more moles. What about decreasing the volume? Which side would that go to? Yep, it would go to the fewer one, yep. Making it smaller, it's whatever side has the smaller volume will be happy. So V is increased, let's see, V is increased, it will form yeah, duh. I'm like, that doesn't seem to look like it. Yeah, V is increased, yeah, it's gonna favor the formation of the reactants. Yep. And you guys told me if we decrease the volume, it'll favor the side that ever has fewer moles, which in this case is the product. But you'll get the same Kc when your dust settles. For such a simple bottom line, that's the way it works. This seems like a pain to pull you through, but I'm going to prove to you that this is how it works. I can't remember if we're increasing or decreasing. Let's just say but which side would be favored if we increase it? Increase the volume. Yep, it'll be, be pulled this way. Yep. So if we increase the volume, it'll go this way. If we decrease the volume, it'll go that way. So if you want to, you can put little subscripts E, like a little E there outside the molar concentration. These are equilibrium concentrations. And sometimes when I'm working up problems for like the test or something, or even homework problems, sometimes I'll put a little E, sometimes I won't. But these are the molar concentrations of these three species, the two reactants and the product, at a given temperature. One of the things then we can do, if we have the molar concentrations, we can slap them into Kc expression and come up with Kc, which is exactly what I've done here. We talked a lot about how do you come up with your equilibrium constant expressions. It's the molar concentrations raised through stoichiometric coefficient. So in front of the NH3, it's 2. From the NH, it's 1. From the from the N2, it's 1. From the H2, it's 3. So we substituted in those molar concentrations. I had to put a little E on, and this is what we come up with. So when we change volumes, this is what has to be our mathematical relationship between the molar concentrations of the product and the two reactants. So let's go ahead and double the volume. Now I have to concentrate. No pun intended. So if we double the volume, those equilibrium concentrations, will they increase or decrease? Like we had NH3 is 0.158 molar. It will decrease, yeah, it'll become more diluted, exactly. So what you're going to see here in a minute is I'm just going to go ahead and decrease the by half. Yep. These all molar concentration cut in half because I'm going to double the volume. You got it. So if I double the volume, if I go ahead and mathematically take each of those molar concentrations, divide by 2, slap them back in my Kc expression, which really needs to be a Qc expression because it's a snapshot, Qc will not equal Kc. Okay, that's exactly what I'm going to do. You guys told me based upon what we know, if we increase the volume, it's going to favor the side that has more moles. You said there's 3 plus 1, 4 moles over here. We have 2 moles over here. So you guys said it's going to go that way. I agree. Oops. Oh, man. Do I not have any bills here? Lordy, lordy. Debate. Anybody got a calculator? Oops. I need to erase that. We got time. We're almost done here, right? Okay, so QC is equal to, somebody take 0.158 divided by 2. could do it in my head if I was Rain Man.
Did you say 1.58?
Oh, 0.158. Thank you. Okay, what is 0.921 divided by 2? 469. Thank you. 461. Thank you. I'll raise that to first power. And then for our H2, 0.763 divided by 2.
0.382.
Thank you, ma'am. We're going to raise that to the third power. Now, somebody put this in their calculator. 0.0790 squared divided by 0.461 for Sierra. Anybody else want to do this?
What's in your slides?
Yeah, I was just reading it.
0.2.
It is?
Yeah.
It's in my slides, but not here. I thought that seemed pretty silly. Oh, wait. What solution?
Right before table 13.1.
Oh.
Yeah. Oh, that's what.
No, it's not. This one. Okay. This is lacking that. So you and I are the only ones that don't have it. I feel legit. So just tell me your number.
Zero.
0.243.
Thank you. I could ask a Sierra too, because you have it too, right? Thank you. Okay. And so what my slides, not these, but what those say, Lindsay, because we're both on the same page here, is we've been talking about if we compare our QC with the 0.0610, what do you think? Our QC is larger than our KC? And if it's too large, then we have too much product, which is the numerator, so we're going to push it that way, which is exactly what we said. That's it. That makes sense? Okay, thank you. Solution, my solution's blank. That is bizarre. Okay. These actually, I like them. It's a nice concise table, but I wish if you would go ahead and take these first two and put a bracket around it, like right this, like bracket these first two. One of the first ways we said we could stress the system was you could add a reactant or subtract a reactant, or add a product or subtract a product. And we talked about this, that's what these first two lines are. They go together. Then if you would skip down to the bottom two rows and put a bracket around these two, okay? Heat is absorbed. Is that endothermic or exothermic? Endo. Yep, this is endothermic. We increase temperature. Okay, we said that actually your KC is going to change. Okay. Changes. Oh, okay, sorry. Oh, they're saying that if we stress it by adding heat, it depends on whether it's endothermic or exothermic, sorry. If it's endothermic, it's gonna proceed towards the product side. You're gonna have more, your KC is gonna be larger. If it's exothermic, then it's going to proceed towards your reactant side, we said, and your KC is gonna be smaller. And then we didn't do this one, but we said, well, what if you cool it down? This is cooling it down. You want to add cooling it down, you could. Heat is given off. Well, it depends on whether your equilibrium is endothermic or exothermic again, but your KC is going to change. And then the last one, if you want to put a little bracket here, between the third and the fourth one, that's what we talked about. And it will favor, if you go clear to the third column then, it favors the side. If you're increasing the bottom, it favors the side with increasing the volume favors the side with, this is a typo. I'm thinking increased volume, this should say towards side with more moles. Typo, Candace.
Otherwise it does the same thing.
OpenStax, yeah. This fewer right here should be more. Increase the volume. And then up here, if you decrease the volume, you're going to favor the side with fewer moles. I'm cool with that. Yep, so we just need to, I wonder if they pay us. We try to correct their mistakes. What do I do here? Oh yeah, okay guys. So we're gonna go around the room right quick. Sometimes this is actually makes it to the test in the form of a question. We have this chemical equilibria. The reactant is going to form two products. They're all three gases, which kind of gives us, we can do a whole KP thing. We can do, changing volume have an effect on the equilibria. Is it endo or exothermic? Wait, we're gonna go around the room. Sierra, endo or exothermic? It is endo. Very good, it's endothermic. So if you wanted to put, we put a heat over here, or energy over here on the reactant side. So here's what the questions look like then. Does anyone have the answers to these?
No.
Okay.
Wait. Yeah, they do. No.
You do?
On the
Yeah,
next slide.
solution.
I'll not cheat, I promise.
Okay. Well, can you see why, and I won't go, we don't have the answer, do we? Yeah. Oh, you do? You do? You don't?
Cover it up with your hand.
Yeah, I was trying to pretend I wasn't. Oh, wait.
No, she
It just says
doesn't.
the same words as the last slide.
Yeah. So, but do you see where, if we add more into O3, where I think of it as pushing, so do we just cycle back around? I don't even have the answers on my slides. You know what? I know what. I am looking at, anyway. So, that will, what's my thing say? It'll go over to the, oh, I'm reading it now. All we're focusing on, and this is the way, thank you, the way test questions often, if you put a little star up to the top of your NO, this is all about the NO. If you add more into O3, it will increase the NO. Sorry, and Lindsay, they already had it, but it will increase the NO. Adding more NO2, would I call that a push or pull? If I was over here, would I call it push or pull? I would call it a push. So it's going to decrease your NO for B. Removing NO2, if I put over here, what I call a push or pull?
Pull.
I would call a pull. So that's going to then decrease your NO for C. For D, let's see, how many moles we got on left and right? How many moles over here? 1. How many moles over there? 2. So if we increase the volume, it's going to favor the product side, so NO is going to increase. Lowering the temperature, so we put heat over here. Lowering means to remove, so to me, if I put heat over here, making it colder, I'm going to actually then pull. And so that's why your NO is going to decrease. And this one, this is right, say no effect. Yeah. Yeah, this one is no effect actually. So we're just adding an inert, a fourth gas, which doesn't react with any of our reactant or two products. And so there's no effect for that one. All right, so you guys should be ready for these. These will be due when?
Wednesday.
Wednesday. Okay, so off to the lab.